Hi, everybody. Thank you for coming on a Sunday morning. I'm quite impressed, to be honest. Today I'm going to talk about techniques and tools and ideas about facial analysis for Python, but not only Python. Who am I? I'm Alex. I work at Cloud Academy, and I'm a software engineer and web developer. I've been working in web for a few years, and now I work as a cloud evangelist for Cloud Academy. So we'll see also about some cloud-based tools for facial analysis as well. So what are we talking about today more in detail? First of all, I want to start with an introduction about what is a face, how do we train a model to recognize faces, what are the edge cases in general. And then I want to deep down in what's the problem, how do we decompose it, and what are the steps to actually find faces and find emotions and find age estimation and all that kind of stuff you can do with a face. And then I want to discuss other alternatives to the do-it-yourself with Python approach, which is great. In some scenarios, it's the only way. But I also want to see what's out there and what we can use, for example, in the cloud, because we love the cloud. First of all, what is a face? Or better, how do we find the faces we want to train our model on? Because there are a lot of faces out there. So these are normal faces. Even just talking about normal faces, you will see there are different, in some cases we have, like elder people with partial information, or we have like obstacles next to the face, or we don't have hair information or glasses, or different lighting condition and shades and color, and it's a lot of data if you want to train a very good model to recognize a face in general. Sometimes you have a background, sometimes you don't. It's a complicated problem, and if you want to build a service or something that works with everyone, especially in a diverse environment, it can be challenging. And these are normal faces, like no edge cases. These are people, and you can clearly see they are faces. As a human, we don't see any problem with this. But there are other edge cases that when you're training or when you are seeing real data, you have to deal with. I wanted to show you a few examples. The first bigger problem is about rotation. We are great, this is still a face. If you show it to a computer, it's not granted that you will see that face. So what about rotational invariance? That's a feature you want to have when you train it, when you train your model, and then when you see new data. But then there are other, even more complicated scenarios. Isn't that a face? Do you think that's a face? Who thinks this is not a face? The face. Great. So would you use that to build your model? Does it make sense? Is that something you want to recognize in your real world application? It's tough. And what about that? That's a face. That's a painting. And to us, it doesn't matter much. But to a computer, that's a totally different data. And what about masks? They are faces, guys. There are so many edge cases that you will probably not use to build a model, but you will find in real world. So it can get very complicated. What about smileys? And that's a face, guys. So it's a big problem, and there are companies that are building tools that will also detect that face. I'm not sure if then the average quality is maintained, but I wouldn't probably use this to train my model. That's your choice. So this is about what is a face and what are the edge cases, and we are lucky enough so that there are tools that don't really need to train a model, so you don't really need a data set to do some of the tasks that we're going to see. And that's where we come with the problem decomposition. So what is facial analysis? What are the building blocks? And how do you build a facial analysis pipeline? So let's see what are the smaller problems that we need to solve in order to find information about a face. The first problem is always finding the face. Without finding the face, you can't do much. And this is known as face detection. It's not about finding out whether it's a male or a female, whether it's sad or happy. It's just about, here is a face. That's the first step of everything. So what's the input of this building block? We have an image. We don't know anything about that image. There could be no face, so that's also a case. We want to find faces. How many are there, where they are, the location, the bounding box, or the landmark points of a face, like where are the eyes and stuff like that. And the output would be a list of coordinates about faces and points and bounding boxes. It's not too hard. It doesn't require a real model. You don't really need to have a lot of data to build something like this. It could be done with computer vision algorithms, which is not really machine learning at all. That's what you find out. Like, let's find a face, let's find some points here and there, like mouth and the nose and the eyes and the eyebrows. How do you do it? Well, there are some algorithmical techniques that are based on, image analysis and window analysis, and I'll show you a couple of techniques. This is not too smart as an algorithm. It's just image analysis stuff, and it's cool because you can do real-time applications. So I can do a video and then track your face on the video. It's like what Snapchat and Messenger are doing. You can track your face. That's very cool. So one technique is the histogram of oriented gradients. So what do? You check the image on a sliding window basis, and you look at each different pixel and check where the local gradient is. And then you end up with something like this. So I don't know how many of you can see a face there. That's like a face pattern. And then if you recognize that pattern at different resolutions, at different sizes, at different locations in the original image, you're able to find faces, more or less to localize them in the original image. This is one of the techniques, and I've done some experiments. It's cool. You can find your landmark points, and that's the Python version of it. So it's like 15 lines of code. I'm using dlib. It's a Python, I think, C++ library. So basically you have this shape predictor that help you with finding the facial landmarks. So there is 68 points detector that will find these 68 points on your face. This is the single image version, but you can easily apply it to a stream, to a video. So each frame, you do the same, it's real time. It takes like 1 millisecond, not even. So you can really do. Well, this is interesting because you don't get just the location of the face overall. You get a set of 68 points here. And with those 68 points, as I mentioned here, you can do even more advanced analysis. For example, if you compute the average and then build a vectorial representation of the face, you can do face recognition, face matching, face comparison, and eventually even based on, when you do different emotions, when you act like you are happy or sad, those vectors, their points, would move around, and you can use the relative location to the norm to eventually estimate sentiment or emotion. Well, this is like that file was built, and it's a lot of data. It's like 100 megabytes of stuff, but still, it allows you to do very powerful real-time analysis. So this is done with OpenCV, Open Computer Vision, and dlib. Then there are other techniques. For example, the Haar cascades. So this is more like scanning the image and looking for pixel gradient patterns, more or less. It's not too different. This is a bit more like you could potentially recognize anything. So you can build a Haar cascade for a car and recognize cars. You can build a Haar cascade for a face and recognize faces. These like huge XML files that you can build yourself. It's not an easy thing. I wouldn't do it, but you can do it. So for example, I found a cascade filter for faces and a cascade filter for eyes. And then I just use them. So I can locate my face, and then within that square or rectangle, I can find my eyes. So for some other applications, you don't have 70 or 60 points. You just have the location of a face and those eyes. But this is really, really fast. You can do it like 20 frames per second on a video. This is powerful. And as you see, you're just using, sorry, the slide is cut, but you can use this phase cascade, just detect multi-scale. So it's already scale invariant. It's not rotation invariant, sadly. But eventually, if you don't find anything, you just rotate the image and keep searching. That's a workaround. Here I'm not doing it, but yeah, this is also the single image case. You can apply this to a video stream as well, and it will work more or less in real time. It's amazing. So this is me with the previous technique doing some very scientific stuff, and the mask works. That's right. I think that's interesting. So you have these 68 points, and we're just locating the face, but with the same data. As a second step, we could use those points to find more interesting information about that very same face, like age or gender or emotions and stuff like that. Let's go on. So this was the first step, face detection, and then you can do, more useful or interesting stuff like face recognition. What's recognition? It means I can see it's you. I can recognize your face. I can take two faces, check if they are close enough to each other, and recognize you. So you can do like face-based authentication, or like if you have a door at the office, you just stand there and door will open. That kind of interesting things. If your input data set is like 20 people, you can even do it without storing too much stuff into databases, or it can be fairly simple. So what's the input? Usually you have two faces, because it makes sense. One or more faces, let's say. One reference and one target. So as a general problem, you want to have two faces already detected and try to find out if they match or not. Eventually, if you have a database of faces, as I mentioned, you can use that list of already detected faces to see which one your input image is matching. So that's a more interesting application, but the technique is the same. So this is a bit harder. It's not super difficult, and again, you can do it without training any model. This is computer vision stuff. It's just algorithmical. The output would be a list of potential matches. Of course, you have a degree of confidence. So you can say, these two faces are 90% apart, 90% close to each other, so they're probably the same face. Then you do your tuning. So how does it work? Well, you want to take those 60, 70 points that we found at the first step and use them to build a representation, a vectorial representation of your face. Usually, you want to use them to build a very high dimensional representation, like the tools that I found used at 128 dimensions vector, like 128 numbers, to represent each single face. And it's interesting because the tool I've used, they used deep learning to find out what that 128 dimensional representation should be. So you don't want to find out yourself. You build some kind of smart network that will take different faces as input and find out which numbers, which computations, which numbers to put together to make sure that two similar faces have a very similar vector in that space, which is huge, but it allows you to do very simple similarity, like distance of faces. So you have two vectors, a lot of dimensions, but you can see if they're close enough. Imagine it's a 2 dimensions vector like this, and you can just find out about for example, the cosine distance between them. And it's more or less the same with faces. So once you have this very highly dimensional representation, you can find out about facial distance and see, okay, this face is close enough to be the same person or not. Of course, there is a tolerance. So when you build a model, when you build a system, you want to tune that tolerance to avoid false positives. If it's an authentication system, you don't want random people to get in just because they are similar enough to your employees, or, for example. False negatives are usually accepted because if you have a stream or something like that, you will have a lot of sample as input, and if you have enough input, the tolerance at some point will be covered and you're good to go. You can't really see it, but this code is doing what I just said. So I got an image of myself, Alex, and that's my input, my reference database. So it's one face database that's able to recognize Alex. And then I take someone, in this case 2 people, and I look for faces. And you can't really see it, but here I'm writing Alex, here I'm writing unknown, because that person is not in the data set. So even with multiple people in the same image, you can say this is Y, this is X, or this is I don't know who. And that's interesting. This is real time as well. This was a video, and I took a frame of it. So this is how you would do it. So in this case, I'm encoding the input face, and that's the reference data set. And then I read another image. I find faces. I encode them. For each encoded face, I compare them, and then I see if there is any match. It's probably me, because it was just me in the data set. And if you have more people in the data set, you want to see who the match is about, who was found in the target image. Same, you can do it with videos too, and most of the time you want to build some kind of API that will tell you, yes, this is authenticated or not, or this is allowed to be here or not, or some more interesting thing that's just plotting a name on an image. But this is the technique. So here I'm using face recognition. It's a open source library that's based on OpenCV and dlib as well. And under the hood here, this compare faces thing is just using the norm of the 2 input vectors. So there is a reference face, a list of potential matches, potential faces that you know exist, and it will give you a list of matches depending on the tolerance that you set. Here the tolerance was like 80% or 90%, so you're pretty sure it's a good match. But you can customize it. And by the way, it's like I don't know, like 1,000 line repository. You can build yourself and just use it as a reference eventually. What about facial analysis? Okay, so far we haven't really done any analysis. So we have built tools and algorithms and detection stuff to analyze the image and find faces or find out if they're similar, but it's not smart. It's not real machine learning or AI or anything. What about facial analysis? Where the input of facial analysis is usually a face. So you know there is a face somewhere. You want to extract higher level information like gender, age, emotions, if there is glasses or a headwear, a hat, or things like that. And this is a bit harder because this is building a model. This is having a training data set, finding out what are the parameters, and having a pretty diverse data set, as I mentioned before, because you need different ages, different genders, different ethnia, whatever. And people with glasses, people without glasses. It's a lot of data to train. You can do it with tons of models, but this is harder. And you would probably start from the same data, like the vector of, I don't know, 60 or 70 points, and use those points to build many models. It's not one model that can do everything. You probably build a model for gender, a model for age, one for emotions, and you can find out more data or more higher level information that you want to find out over time. So if you have a facial analysis tool or service or pipeline, you might want to do all this computation in parallel, for example, and then make them converge to like a full information stream. So what are the key points? Like, how many training sets do you need? Is it a huge one? Is it one for each model? Can you share the data sets between different models? That's a tough problem. I haven't worked on this really. How do you do feature extraction in parallel? How do you predict or classify or whatever you're building in parallel? And what about accuracy? Is it objective, subjective? Is emotion the same in everywhere in the world? Is age different in different locations of the world? It's tough to build a general model for this kind of higher level, very subjective kind of information. And also real time is not really guaranteed. It's not just parsing some pixels and see like distance of 2 vectors. You need to train them. Maybe you have a huge model, or you need to work with matrices or have a neural network compute some stuff, and you probably can't do real time. So this is more suitable for like a service. You give the image, they give you some information, and you probably don't want to work on video. If you want to do all of this in parallel for a stream of 10 seconds of video, it might take, I don't know, half an hour. It's not real time. Depends on the model, of course. So what I've shown you so far was built in Python. There are libraries, there are tools. There is a lot in the open source world. What's out there? What other services are there so that you don't have to do it yourself? So I work at Cloud Academy. We use cloud computing services a lot. And I want to talk a little bit about some services that can do facial analysis. So they usually give you detection and matching and even searching on a data set. For example, I will focus on these 3. These are actual cloud computing platforms that offer a wide range of services. So it's Amazon Web Services, and this is Google Cloud Platform, and this is Microsoft Azure. There are other tools that focus just on facial analysis, like Face++ or Kairos or AMO View. And those are good services too. I will say they don't have an ecosystem of services around this facial analysis thing, which means maybe you have to deal with storage yourself, or maybe you cannot build a full pipeline automated. So I would recommend you to go with a full solution, cloud solution, so that you can have your virtual machines, your instances, your storage, your code deployed somewhere, and you can put all together to build your application. So what can you do with these guys here? So this is Python. Of course, they have a nice client for Python. This is Amazon recognition, and you can detect faces, and you just provide an input image. You usually store your images in some kind of object storage, like S3 or Google Cloud Storage. In this case, it's Amazon S3. So I stored my face in my bucket, and I will detect faces. And in your response, after a while, you will get your face details. So it's a long list of faces with everything I've just shown you: age and sentiment and headwear and where is the face and all the points that you need. And you can eventually provide different resolution, different detail levels. So it could be, oh, give me everything, or just give me the points, or just give me the emotions. So you can usually optimize the API calls for your needs. And it's 5 lines of code. It's not too bad. Same with Google. It's almost the same code. It's Google Vision.images.annotate. This is a bit more powerful. You can annotate multiple images in the same API call. It's sometimes interesting if you have a big data set to get started with. It's the same. You store your my face in a Google Cloud Storage bucket. It's almost identical to Amazon S3. And then you specify which features. So with Google Vision, you can do label detection and logo detection and text extraction. You can do a lot of stuff. In this case, I am asking just for face detection. And I'm saying just give me the first 10 faces, because it takes almost linearly longer if there are more faces in the image to compute. I can imagine why. And again, you will get a response maybe in 200 milliseconds, 300 milliseconds, and you will have some face annotations with the features that you requested. There you go. So the third one is Azure. It's from Microsoft, and they really shrink the, the lines of code you need. So you just import it, give it even a URL wherever your image is, and you will get face detected as a list of faces. I've played a little bit with the first two. They're very powerful. They do different things. Google is not really good with emotions recognition. Is super cool because it's rotational invariant, and it's really fast. And now it gives you age and gender and all the information you would actually need for a real-world application. Google is really bad with emotions. It's like 3 emotions, and they're always wrong. But it's really cool for location. It gives you a lot of points, and it's cool for like also text extraction and logo detection and other interesting features that you may want in your pipeline. I haven't played much with Azure, but they are pretty good with this machine learning stuff, so it's worth having a look. What about features? You can see it. Yeah. So we talk about face detection. We talk about recognition, which is I have 2 faces. I want to see if they are close enough to be the same face. And all of them, but Google Vision doesn't support comparing 2 faces. But let's say detection and emotions are in common with everyone. Amazon is been adding a lot of stuff about that higher level information like age and gender and hardware, and if you are smiling, they will tell you if you're smiling or not with the confidence level. And what Amazon has built is interesting because you can do recognition and search. So you can say index these 200 faces in your face data set, in your face index, and then you can just say, this is a new image, tell me if it matches any of the faces I've indexed so far. So you don't really have to build your database, your data set, and keep those big arrays in memory or in storage. And it's an interesting service. And also Azure supports everything. It's super cool. And they also support video. So you just give them a video and they will do the same. They will return a list of lists of faces. So why would you do this? Why would you use services instead of do it yourself with Python? Well, in some cases, you really have to use Python. Maybe it's an embedded system. Maybe you don't have network connectivity. But if you do, what are the pros? Well, it's agnostic. You have SDKs for any language. That's an interesting feature. It's just RESTful APIs. And then all those models that I talked previously, maybe they will be updated over time. You don't have to constantly improve the system yourself. They will update the model and add new data and retrain everything and improve the accuracy, and you just keep using the service. That's another interesting advantage. And of course, you don't need to manage any infrastructure. So you just have this API, you call it. They have some kind of SLA, so they will not reply in 30 seconds. It's usually 500 milliseconds to a second, depends on your network and on the size of the input image. They recommend some kind of minimum requirement to detect faces. So if a face is smaller than 100 pixels per 100 pixel, it's probably not going to work. But that depends on your data. And then, of course, the model is pay as you go, and you usually have a free tier. So you can say, I pay for, I don't know, $1 for 1 million images. And if you don't use it, you don't pay anything. If you use it 10 times more, you pay 10 times more. And you, again, usually have, I don't know, 1,000 images per month for free. So you can start playing with this stuff and not pay a single euro or dollar. So embedded systems are a bit different because it's a great scenario because you don't have computing power on those devices. It's also a problem sometimes because maybe you don't have a good connectivity. So it really depends. Like if you are building a robot, you know, Google Vision and recognition have been announced with this in mind too. So you're building a robot and you want to give it vision. That's why Google Vision was called like that. It will give your robot some vision capabilities, but you have to have good network connectivity. You have to be able to take images and upload them, which maybe you will need to shrink them before uploading. It can get tricky if it's an embedded system rather than a website or a mobile application. But still, it's a great use case because you don't want to deploy, I don't know, a gigabyte of model on a single embedded device. And then let's say that accuracy is a bit more granted. So the screenshot I showed you about my phase or my experiments, they were not picked from a big set of things that didn't work, but let's say that you have to tune parameters yourself depending on the input size of the image, and then it doesn't work with rotations, the code that I showed you at the beginning with OpenCV, and maybe it works with normal faces, maybe it doesn't work with the smileys or with the paintings or with the animals that I showed you, while with these cloud services they are covering more or less everything you need, and they will update what is supported over time. So it's an interesting thing. What about the cons of using a cloud service? Again, can be real time. If you want to show a cool video like on Snapchat, the Snapchat thing is not computed in the cloud, it's computed on the device because it must be shown in real time to the final user. So if you may need to actually deploy or embed your model in the device, if you want to do real-time stuff, this is a big limitation. And of course, you always need connectivity, pretty good one. Another cons is you can hardly customize anything. You cannot say, oh, I want to detect something different, or I want to use a different data set, or I don't want animals. Just don't give me you can't do that. You can't really customize the training set or the model or the output. It's a service, I'm sorry. And yeah, the model is a black box. So you have no idea what's out there unless they tell you. Sometimes they tell you. So for example, Amazon Recognition is using deep learning, and probably Google as well, but they will never give you the model. They give you the framework. Maybe they're using TensorFlow, but it's a black box. So it's really up to you, up to your use case, up to your business model, if it's a business application, or if it's a university experiment, or if it is just a cool thing you want to build on a weekend. That's up to you. Thank you very much.
Yes, we have 7 minutes for a question.
Yes, I have a question. Have you ever tried to use a pre-trained model from ImageNet? I mean, many university train deep learning models, and they make it available for free to use, like Model Zoo for Cafe or stuff like that.
Yep, that's how I would do it, because I don't want to build a 1 trillion images data set to train a cool model. I would do exactly that.
Okay. My question was if you have
I've tried to use them. I didn't have enough data to show like what's better or not, so I didn't include it.
Oh, okay,
but yeah, that's a good suggestion. Any other question?
What's the minimum amount of pictures that you can start using to start experiments and start to learn? What's
minimum
the
amount?
Yeah.
1.
Oh, really? Okay.
To start playing and experimenting.
In order to recognize faces, like recognize, for example, for start 3 or 2 different faces. So not just detecting, but to recognize different faces. 2.
Unless you have more than 1 face in the same image.
Something that I could have.
Because you're not building a model. You are using computer vision and like algorithmical stuff, and you don't really need a training set or anything. That's the cool part of detection and recognition. Any other question? Yeah.
Do you know what the data policies is of these services? I mean, because you upload faces and then you might upload also other data of these people. I mean, is it safe to use these services?
Well, they say they don't store your images, they don't store your faces. They build those vectorial representation, then they just store that. But if you use this kind of services, you are already uploading your images in their cloud storage. So if you don't trust them, if you have a privacy problem, it's a mindset problem, not a security problem. But yeah, they are guaranteeing a higher security level. And they're not storing the images. They are just doing
representation.
Yeah,
okay.
exactly.
Okay, thanks.
No question?
Just a clarification on the previous question. So they're not storing includes they are not using it to enhance their models, basically, or it's a different thing.
I don't think so. I don't think they're using what you provide to build a better model. I'm not sure they can. Maybe they are, but what they say is we'll never store your images for internal purpose. They are computing it, taking the vectorial representation, and then it's gone. So if you upload the same image, it will take the same time. They're not caching or anything. They will just. I don't think they are using it because you probably need some labeled data to actually train such a model. So you provide random stuff, and maybe they will not use it. I uploaded a lot of random stuff. I hope they didn't use it. Okay. One
Another
more.
question? Yes.
So of the stuff you've tried, what's the best at like emotion recognition, emotion detection?
So far, Amazon recognition for emotions. They have a wide range, like 6, which is probably the universal emotion set, while Google is using a subset, and it's not really accurate, and they would predict only 1, while Amazon can tell you, okay, this phase is 20% sad and 15% surprised, which is a better way to give you some freedom to do what you want with that data. Thank you. Any more question? Okay.
You said that among the cons of using cloud services, there is the fact that machine learning algorithms are like a black box. Is it totally true? You have no chance of changing some parameters?
You have, sorry, that's a good question. You can change what you're asking for, but you cannot change the model. You can say, okay, give me only the first n images which have a high a confidence higher than 80%, but that's not changing the model. That's filtering the results, more or less.
So thank you, Alex.
Thank you very much.
Casalboni.